Next topic is Dirac notations, Dirac bracket notations. Uh, the physical state of the system represented in quantum mechanics by elements of linear space that are belongs to Hilbert space. These elements are called the state vectors. Elements of linear so that are belongs to the Hilbert space. These elements are called state vectors. Dirac introduced the symbol like this is called ket vector. So we know normal vector in if you take the three-dimensional vector, for example, I can write here this is a vector. So this a vector is represented ax plus ay, ey plus az and ez. Here ax and ay and az are called the component of the uh, vector. These components are depends upon the choice of coordinate system. So here I am taking another vector addition. The vector, if you add two vectors, so this is A vector and this is B vector. I am going to add these vectors. This one is A, this one is B, and resultant is C vector. So this is also the vector, and this addition system independent of choice of coordinate system. So the vector represented by the A three-dimensional vector ax cap plus ay cap plus az ez. Here ex, ey, ez are the unit vectors. So the state vector is represented in quantum mechanics like this ket vector. So these ket vectors are written in terms of the column vectors in matrix from ax and ay and az. Here these ax and ay and az are the component dependent on coordinate systems. This component dependent on coordinate system. And this is the abstract space vector, and this vector is the independent of the choice of coordinate system. Simply the state vector ket. This is introduced by the Dirac. We can call the ket vector or simply the ket. It is denoted by the state vector. So which will take in the different forms. For example, here I am taking A like this, and this is also one more form. For example, this is the set of uh, vectors. For example, wave function psi1 of x, comma psi2 of x, and so on, psi n of x. Then here I'm going to take different forms in a different representation to distinguish the ket vector corresponding to the different states. So here the different states are there. So I'm going to write this one like this: psi n of x into ket vector, or I'm going to write this one like this. Here the n is a, these are the psi n of x is the set of vectors, and n is the subset of the vectors. Corresponding to every vector, uh, this is the vector, is defined a conjugate vector also. It is denoted by A complex, for which Dirac used the notation like this. Which is called a bra vector, or simply bra. The conjugate of a vector is a bra vector, and vice versa. So this notation is designed from the bracket notations. So the letter bracket by dropping the C They are designed like this. So this one is a ket and this one is a raw vector. The word bra and ket uh, were designed by the this bracket code. So in quantum mechanics, normally uh, we represent the state vector like this wave function psi, which means this is the ket vector. And the complex conjugate of this vector is denoted by the raw vector. The inner product of the two vectors is denoted by like this. When ket is multiplied by the complex number, we can get. So here the some important properties of Dirac bracket notation. One is when a ket is multiplied by complex number, we get also a ket vector. For example, A and B are complex numbers. So we can write this complex number like this. A wave function psi we can get complex number and this same complex number multiplied by the raw vector, sorry, raw vector, we can get complex conjugate of the complex number and this vector. And second property is the for every ket there exists a unique bra and ket vice versa. So there exists a ket and also there exists a bra also. Like wave function, second next properties like wave functions. Now kets are Elements of a Hilbert space. The bra vectors belongs to a Hilbert space. It is denoted by H complex. This is the H, which is said to be the dual space of the Hilbert space of a ket vector. And one more properties of Dirac notation. So to every ket, this is the ket vector. The corresponding bra vector, so which is given by the following condition. If we have ket vector can give some complex conjugate, it will turn into the bra vector. Or A ket vector is there. If I give some complex conjugate, A complex, and this ket vector is turned into the bra vector. Similarly, A wave function psi, we can write this notation A into wave function psi. And bra vector A wave function psi equal to A complex into wave function psi. And the next property is scalar product. We already discussed scalar product. So here I'm going to write directly wave function psi, phi and psi whole complex equal to, if you apply this complex, this ket will turn into the bra vector, bra will turn into the ket vector. So if psi is multiplied by the same state, you can get norm of this condition. This norm is always greater than or equal to 0. So norm is always real and positive. So norm is real and positive. Next one, normalization. So wave function psi and the same wave function, if it is equal to 1, then we can call the orthonormal state. If pi and psi are orthogonal, then we can write like this: two different state of the system equal to 0. Then we can call the state orthogonal state. And the last two properties are, one is and the last one property is the triangle inequality property. So that is the root of wave function psi and pi. This is one state and other state like this. Root of so these are the properties of the Dirac notations. So Dirac introduced one notation. By using this notation, we can call this a ket vector notation. The state vector in quantum mechanics represented by this symbol, the ket vector. And the complex conjugate of the ket vector is represented by draw vector. So this is the all about Dirac notations.